Good evening, friends. In this video, we will solve some gate questions that have recently asked, means the GATE 2020 questions on electromagnetic field subject. So we'll solve those questions by using our conceptual knowledge. So as far as the questions are considered, the GATE questions in 2020 on the subject EMF or electromagnetic fields is a little bit easy questions. Now I will solve one problem. First problem is, in the question it is given that a long wire carrying a current of 2 amperes and it is extended from minus infinite to plus infinite. Means an infinite current carrying conductor. The meaning of this is infinite current carrying conductor which is extended from Z is equal to minus infinite to plus infinite, and it is carrying a current of 2 amperes. Near to that you have a loop, a conducting loop of 1 meter side. Now the question asked in the examination is to find the mutual inductance between the long wire, this one, and the square loop, this one. It is asked to find the mutual inductance. Generally, if you know the expression of the mutual inductance between a long wire and a loop, then you can directly substitute the values in that expression. But in general, we are not familiar to those expressions. Hence, we will use the basic concepts of magnetostatics in order to obtain the expression of inductance and then substitute the values in those expressions. Now, I am using the basic. See, if you don't know the expression of inductance, or if you don't remember the expression of inductance, then there is no problem, because there is a particular procedure in order to obtain the inductance. That particular procedure is, first of all, we will find the flux density B, then we will find the flux phi, then we will find the flux linkage N phi, and by taking the ratio of flux linkage to the current, we will obtain the inductance. This is a 4-step procedure which is commonly used in order to find the self-inductance as well as the mutual inductance. Here, as it is asked to find the mutual inductance, what we need to know is the flux produced by the current carrying conductor linking the conducting loop. We need to consider that flux. So here, in order to find the flux produced by the current carrying conductor, from the right hand thumb rule, we know that the flux due to a current carrying conductor which is carrying the current in Z direction is always in phi direction. Hence, this is obtained from either from Biot-Savart's law or from Ampere's law. We can obtain the flux density due to a current carrying conductor which is a long current carrying conductor like this. B bar is equal to mu naught is nothing but the permeability as the medium in between the current carrying conductor and the conducting loop. The medium is air, hence I am taking mu naught as the permeability of air. And it is mu naught I by 2 pi rho. Rho is nothing but the perpendicular distance from the current carrying conductor to the conducting loop or to any point of interest. And it is A phi bar. Phi direction is this one. If the current is flowing in this direction, the flux will flow in this, will be created in this direction. This is according to right hand thumb rule. So it satisfies the right hand thumb rule. As you know the B easily, you can obtain flux from B by taking the surface integral of B dot ds. So as it is in A phi direction, you need to consider another surface which is also in phi direction. When you want to select the surface in phi direction, it must have 2 variations. One is the rho variation and Z variation. So by simplifying this, you will get mu naught I by 2 pi out of the integration, because for this integration, the variables are rho and Z. When compared to this integration, mu naught I by 2 pi is a constant, so I can take it out from the integration. 1 by rho d rho. 1 by rho d rho integration is ln of rho and integration of dz is z. Now how to take the limits of this rho and z? It depends upon the distance to which means the distance between the current carrying conductor and the current carrying loop. Based upon this distance, you need to select the rho limits. If you consider this side is at a distance of 1 meter from the current carrying conductor, hence the initial limit is 1. And this side is at a distance of 1 plus 1, 2. Hence the upper limit is 2. And this is the initial limit because the variation of z for the conducting loop is from 0 to 1. Hence I took z is equal to 0 to 1. By substituting the required values, see, this is the flux phi. This flux is created by this current. So the ratio of flux linking the second conducting loop to the current of the first conductor. I is nothing but the current of first conductor. So we don't bother about whatever may be this current. It depends upon how much amount of flux linking the second conducting loop. So by taking the ratio of the flux linking the conducting loop to the current flowing through this conductor, we'll get the mutual inductance. If the flux and the current are related to the same conductor, then it can be treated as a self-inductance. Otherwise, it is a mutual inductance. Now, by substituting mu naught value and sending this I to here, you can simplify this as like this. And in the question, it is asked to express the inductance in nanohenries. Hence, if I want to express this in nanohenries, I can express the mutual inductance as 138.6 into 10 power minus 9 henries, which is nothing but nanohenries. This is the answer for the question to find the mutual inductance between the current carrying conductor, an infinitely long current carrying conductor and a conducting loop. So in this way you can find